Welcome to an overview of two powerful tools, R Markdown and the R Project. These are essential for modern data storytelling. Your data tells a story. R Markdown helps you tell it, clearly, reproducibly, and beautifully. But first, let's look closer at what R Markdown is and why it's a game changer for data communication. R Markdown is a dynamic authoring framework that seamlessly weaves narrative text and code into elegant output. It allows you to analyze, share, and reproduce your work easily. R Markdown supports multiple languages like R, Python, and SQL. You can choose from dozens of output formats, including HTML, PDF, Word documents, interactive dashboards, and presentation slides. Now, let's shift our focus to the R Project, the core engine behind R Markdown's power. R is the free software environment for statistical computing and graphics, a vital tool for data scientists globally. It's open source, highly versatile, and compiles and runs efficiently on various operating systems, including Unix, Windows, and Mac OS. To get started, you can download R from CRAN, the comprehensive R archive network. Just choose a mirror, install, and begin your journey. Why should R be your go-to environment for statistical computing? It offers immense value to the data world. R empowers reproducible research, advanced graphics, and access to cutting-edge statistical methods, all backed by a strong community. The R Foundation is dedicated to supporting R's development, conferences, and global collaboration, ensuring R's longevity and quality. The combined power of R and R Markdown has a profound real-world impact across diverse fields. R Markdown is used everywhere, from publishing scientific articles to creating dynamic business dashboards and reports. Similarly, the R Project powers discoveries, provides insightful dashboards, and drives crucial data-driven decisions across the globe. R is more than a tool. It's a movement. R Markdown transforms your analysis into compelling stories. Explore, create, and share with confidence. Welcome to First Steps in R, Statistical Computing Fundamentals. R is a powerful language for statistical computing and graphics. Let's take our first steps together in mastering this essential tool for data analysis. First, let's look at how to get help and explore objects within the R environment. Need help with a function? Just type a question mark followed by the function name, like mean, or use the help function. To understand your data, use str to see an object structure and class to check its type. Next up is learning how to manage packages and load data effectively in R. Install necessary packages with install.packages, and then load them into your current session using the library function. Load built-in datasets easily with data. For example, data, iris, brings the famous iris dataset right into your environment. Understanding your working directory is crucial for managing file paths and data access. Use getwd to check your current working directory, and setwd to easily change it to where your files are located. Now let's delve into vectors, the fundamental building blocks of data structures in R. You can create vectors using C to combine elements, define sequences with the colon operator, or use sequence and replication functions like sequi and rep. Manipulate vectors using functions like sort to order elements, table to count occurrences, rev to reverse the order, and unique to find distinct values. Mastering the selection of elements and using conditional logic is key to precise data manipulation. Select elements efficiently using brackets. Filter by position. Use negative indexing to remove elements, or specify ranges to extract exactly what you need. Compare values with operators like equals, 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 less than, and greater than. Also, check for missing or null data using is.na and is.null. With these first steps, you're ready to explore R, install packages, work with data, and build your own insightful analyses. Happy coding! Welcome to R3, Parameters, Variance, and Confidence Intervals. This video is the third in our Getting Started with R series. We are going deeper into statistical thinking using R, adapted from M.J. Crawley's Statistics, an Introduction Using R. Today, we're focusing on how to estimate parameters from data, understand variability, calculate variance, and build confidence intervals. Our focus areas today include estimating parameters, understanding variance, and constructing confidence intervals. Before you dive into the code, you must first ask yourself the right questions about your data. First, identify your response variable. which is what you are trying to predict or explain. Then, identify your explanatory variables, which influence the response. Next, determine if your variables are continuous or categorical. Continuous variables can take any value, while categorical variables fall into a limited number of categories. Finally, classify the type of response variable. Is it a measurement, a count, a proportion, time to event, or a category? Now, let's talk about the sample size, denoted by n, which is simply the number of observations in your dataset. The sample size, or n, is a fundamental concept. It represents the quantity of data points you have to work with. In R, you can easily calculate the sample size using the "length" function on your data vector. Let's move on to central tendency, which describes the center point of your data distribution. The central limit theorem suggests that when you repeatedly sample data, the values tend to cluster around the mean. The mean is the arithmetic average of your data. In R, calculate it using the mean function. The median is the middle value of your ordered dataset, and unlike the mean, it is resistant to outliers. Use the median function in R. The mode is simply the most frequent value within your dataset. In our next session, we'll build on these foundations to explore variability. We will cover calculating variance and constructing those all-important confidence intervals. Welcome to our deep dive into one of the most fundamental concepts in data analysis, statistical variance. Understanding this metric is crucial for making reliable data-driven decisions. We begin by exploring the idea of variation itself, the foundation of all statistics. Variation is the heart of statistics. The greater the variability in your data, the greater the uncertainty in any estimates you make from it. One simple way to measure variation is the range, which is the difference between the maximum and minimum values. However, range is highly sensitive to outliers, limiting its usefulness. To improve our measure of variation, we need a better method to quantify how spread out our data points are. A more robust approach is to measure how far each data point deviates from the mean or average value. By squaring these deviations and summing them up, we arrive at the sum of squares. This calculation, represented by the formula sum of y minus y bar squared, is the foundation of statistical variability. Next, let's look at the crucial concept of degrees of freedom, often abbreviated as DF. Degrees of freedom are calculated as the sample size, denoted by n, minus the number of parameters you estimated from the data key. For instance, in simple linear regression, where we estimate two parameters, the slope and the intercept, degrees of freedom equals n minus 2. In a one-way ANOVA with 5 groups, you would use n minus 5 feet. Now we can combine these concepts into the primary formula for variance. Variance, symbolized as s squared, is defined as the sum of squared deviations divided by the degrees of freedom. Specifically, this is the sum of squares divided by n minus 1 foot. We divide by n minus 1 foot instead of n because we estimated the mean from the same data set. This adjustment provides an unbiased estimate of the population variance. Let's illustrate how variance works with a practical example using a baseball league scenario. Consider League A and League B. They have different average scores, or means, but when we run the variance calculation, they both have an identical variance of 1.33. Now compare League B and League C. They share the same mean, but League C has a drastically different variance of 14.22. This demonstrates a much wider spread in the scores. This practical example leads us to the crucial point of why variance is so important in statistical analysis. Large differences in variability, or variance, between datasets significantly affect the reliability and interpretation of your results. When variances differ substantially, comparing the means of two groups becomes statistically risky because the variability itself might be the most important finding.